So till last class, we have studied the lens formula, then the prisms, then how refraction occurs in the prisms, then refraction occurs in the spherical surface. Then the important topic is the lens maker's formula. So now we are going to see the application of these lenses in some instruments, that is optical instruments. Okay. So where the lenses are used, we know that already in the 10th we have studied the lens is used to correct the refractive defects in the human eye. But this year the topic was eliminated and it's reduced. So in the human eye we have different defects: myopia, hypermetropia, presbyopia. So to correct all the defects, we'll use spherical lenses. Okay. So the lens is not only used to correct the refractive defects in the human eye, also used in some instruments. The simple instrument is microscope. So in biology lab, we'll observe the specimens under microscope, like cell structures, plant cell structures, and blood cells, and some many things, xylem, bloems inside the plants. So and the tomato. So many things we observe under the microscope. So the microscope that magnifies the objects, that enlarge the objects. So a lens contributes to enlarge the objects. So such a lens are called a simple microscope. So now we are going to study about microscope. So what is a microscope? A microscope is nothing but a converging lens of short focal length. A converging lens of small focal length is called magnifier, or it is called magnifier or a simple microscope or microscope. There are two types of microscope we have. One is a simple microscope, another one is compound microscope. What are the two types of microscope? It is classified into simple microscope. The second one is compound microscope. So first we are going to study about the simple microscope. Okay. For a simple microscope, the object is placed very close to the lens, having a short focal length, and the eye is kept very close to the lens on the other side. And we should choose the object must be kept less than or equal to one focal length. We know in general this is a converging lens. It have a two spherical surface on either side, and this is optic center. An imaginary line passes through the optic center, and center of curvature is called focus. Okay, and distance between this focus and this optic center is called focal length. Both also equal. Okay, so this is called a focal length. And object may placed less than one focal length or equal to one focal length at the time where image is obtained. Now we are going to keep the object, that is, the object is placed less than one focal length. So where we are placing object? Object is placed less than one focal length. So by placing object less than one focal length, so object is placed here, assume. So AB is the object. Already we know the effective diameter is called aperture. The first ray incident parallel to principal axis, then it converges a point to principal axis, that is to principal focus. The first ray gets converged to principal focus, and the second ray passes through optic center, but this ray refracted. But the second ray from the object, that when it passes through optic center, it goes straight without any deviation. So how two rays goes? The two rays goes divergent. Okay, the two rays goes diverging away to each other. The two rays goes diverging away. So extend the rays in the backwards. By extending the rays in the backwards, it forms a final image which is same side of the objects. So final image is virtually erect and enlarged. So final image is virtually erect and enlarged. Let us say AB is the size of an object, that is h. What is h? Height of an object. So in this case, when object is placed less than one focal length, it produce virtually erect and enlarged image. Okay. So the distance between object to the center of a lens is called object distance. Okay. Whereas final image is obtained, that is also on the left hand side. So this is the final image is obtained. For that, already I said, in this case, object is placed less than focal length and eye must be kept. Here we must position our eye. So this is eye. So eye must be positioned very close to the other side of the lens. So one side of the lens object is placed and the other side we must keep our eye so that we'll get the clear real, sorry not a clear, a real, so that we'll get a virtually erect and enlarged image. This is virtually erect and enlarged. So virtually erect and enlarged image is obtained. So in this cases, the image distance will be the least distance of distinguishings. Least distance of distinguishings, that is equal to 25 centimeter for comfortable view. For comfortable view, for comfortable viewing the image, the eye must be positioned on at 25 centimeter because our vision starts from 25 to infinite. So less than 25, it's very difficult to identify the object. So the normal near point is 25 centimeter. Okay, this is the least distance of distinguishing, that is mentioned as D. Okay, so in this case, we are going to find the magnification. What is the magnification? This is a linear magnification. We can find a linear magnification. The linear magnification of this case, that is simple microscope, is already we know the linear magnification. What is the linear magnification? It is the ratio between image distance to object distance. Also we can write it as V into 1 by U. But V into 1 by U, we can write it as from the lens formula. What is the lens formula says? Lens formula says 1 by F is equal to 1 by V minus 1 by U, or 1 by U alone you transfer, both the terms you transfer. So 1 by U is equal to 1 by V minus 1 by F. So instead of 1 by U, we can write 1 by V minus 1 by F. So from lens formula. So from lens formula we alternated this. And now you multiply this inside. What you will get? V by V minus V by F. That is V by V is equal to 1. So 1 minus V by F. Use sign convention. Using sign convention, image distance is minus V. So instead of already one minus is there, now we are using the sign convention. So how it changed? So M is equal to 1 minus of V by F. So minus into minus become plus V by F. So we got the magnifications. Okay, already this image distance, which is equal to least distance of distinguishing, that is M is equal to 1 plus V by F. So this is a linear magnification in the simple microscope, because in this case image distance is equal to D. So hence we obtain the magnification in the simple microscope. This is linear magnification. So the linear magnification for the conditions object is placed less than one focal length. But some situations it is image is obtained at 25 centimeters. So somehow you feel the strain. To avoid straining the eye, the object must be placed at F for comfortable viewing. Okay. In that cases, it may create some angle. So the magnification is differ comparing this case. Okay. So that is the angular magnification. So in this cases we found a linear magnification. In that cases we are going to find an angular magnification. So how to find the angular magnification in simple microscope? That we are going to see. So for that, first we'll draw a ray diagram, because at 25 centimeter eye may feel somehow strained. So to avoid straining the eye, the object must be placed exactly at the focal length. This is optic center, aperture, first focal length and the second side focal length, and the object is placed exactly at focal length, focus, principal focus. So it's first focal length, f1. So the first ray, which is incident parallel to principal axis, then it converges through principal focus. Second ray goes through optic center. And two rays must go parallel to each other. Yes, the two rays must go parallel to each other. So the final image would obtain at infinity. So final image would obtain at infinity. So this is our eye. Okay. So AB is the object, and the AB is an object. So that height of an object is h. Here, in this cases, the incident ray from the object, which makes an angle to the principal axis, angle subtended by object. Similarly, image is parallel rays. No, so to parallel rays meet at an infinite. So it is enlarged. So the image forms an angle from the rays theta O. That is angle subtended by image. So here h is height of the object, and the theta O is angle subtended by object, and the theta I is angle subtended by image. Angle subtended by object and angle subtended by image. Okay. And then so here we can find one more thing. It's angular magnification. If object is placed to D for a comfortable viewing, if object is placed at D for comfortable viewing, then it makes an angular magnification. See, the angular magnification looks like this. This is principal axis. AB is a size of an object, that is equal to h. This is a ray from optic center. It makes an angle theta O. So here the angle is theta I. Okay. So the angular magnification for this case, it is a ratio between angle subtended by the image to angle subtended by the object. Okay. Also the angles, but tan theta O already we found it is h by d. See, it is equal to h by d. Tan theta, no, it's a right angle triangle. So tan theta naught, that is a theta O, angle subtended by object is equal to opposite by adjacent. Similarly, angle subtended by image is equal to h by f. So substitute in these cases. So what you will get? H by f divided by H by D. So H and H cancel. So finally, the magnification M is equal to D by F. So hence, we obtain the angular magnification. So the angular magnification of this case for a comfortable viewing when the object is placed at a D, which is equal to distance of distribution by focal length. Okay. So this is one less than the magnification. This is one less than magnification when image is at near point. When image is at near point. Normally for simple microscope, the magnification should not exceed more than or equal to 9. So this is a limited magnification. So simple microscope have only the limited magnifications. So the magnifications may equal to 9 or less than 9, within 9 only. So no magnification in a simple microscope exceeds more than 9. So based on this, we'll see the simple problem. So in that, okay, already we know M is equal to 1 plus B by F. Okay. So in this cases, if the magnification is 6, what would be the, if magnification is 6 times, find the focal length of this converging lines in the simple microscope. Okay, if magnification is 6 times, find the focal length of this case. Already we know the distance of least distance of distributions, that is equal to 25 centimeter. So directly we can find. So M is equal to 1 plus D by F. M is 6, D is 25 centimeter. Therefore, we want to find the focal length. No. So 25 by F is equal to 6 minus 1, which is equal to 5. Therefore, transfer this both. 25 by 5 is equal to F. So 5 centimeter, which is equal to F. So it has a shorter focal length. So already I said a microscope is nothing but a converging lens of small focal length. So here also we got a short focal length. Okay. Suppose a particular magnifier, simple magnifier, that is microscope, have magnification of 6 times. Then what would be the focal length? So we can get from the linear magnification. So according to linear magnification, it is 1 plus D by F, that is the distance of distribution by the focal length. Already we know this is a constant value 25 centimeter. So directly we can find the focal length. So in a simple microscope, the converging lens that should have a short focal length only. Okay. Next we are moving to the compound microscope. Okay. Till now, simple microscope we have studied, but the simple microscope has some limitations. It has a magnification up to 9 times. So it uses only a single lens. So a converging lens, to a converging lens, the object is placed at one side that is equal or less than one focal length, and eye is kept on the other side, which is very close to it. So hence the object may be enlarged maximum up to 9 times. Suppose a person who needs an object to be magnified larger than a simple microscope, he must need a 2 lens system. Okay. In a lab we are observe the specimen under microscope. No, that is not ordinary microscope, that is a compound microscope. So such a microscope have a 2 lens system. In that one is compounding other. Okay. So it is called as a compound microscope. So second type of the microscope is compound microscope. So according to compound microscope, if one wants larger magnification, he must use 2 lens system. In that one is compounding other. So in that one is compounding other. Such a microscope is called compound microscope. Now, how the image is magnified in the compound microscope we are going to see. Listen it very carefully. Okay. So for that we need a two lens system. In that one is a shorter focal length, another is a larger focal length. So this is the principal axis. So on a principal axis, an objective lens is placed having a short focal length. Okay. So first we place the object. The object is placed between f and 2f. If object is placed between f and 2f, that is AB is an object. AB is an object. From the object, the two rays start. First ray, which is refracted through focus, and the second ray goes through optic center. So the final image is obtained here. Final image is obtained here. So in this case, the image formed by the objective lens. So this is objective lens, and the position of object from the objective lens is object distance. Then optic center to the focus of the objective lens is focal length. So FO is the focal length of objective lens, and image, final image is obtained here. So B dash A dash is the image by, not a final image, first image by the objective lens. This image that acts as the object to the second lens. So the second lens is separated from the objective lens, which is far away from this. Okay, so h is the height of an object. Here, then what happened to the rays? This object that produce so the final image is obtained here. Okay, so final image is obtained at the same side of the object, which is enlarged. So the enlarged image is obtained on the same side of the object. Okay, so this can be observed under our eye, and this is eye lens. So this is eye lens having the focal length, it is FE. So the distance between center to the focus is called focal length of eye lens, and the remaining distance, that is a distance between principal focus of objective lens to principal focus of eye lens, is called tube length, that is denoted as L. Okay, I repeat once again, we have a two lens system to get a larger magnifications. First lens is objective lens, and the second lens is eye lens. Here objective lens have short focal length. It is taken short focal length, and the eye lens is taken as a large focal length. Okay, so the first objective lens that forms the enlarged image, so that image serve as an object to the eye lens, and the final image is obtained, that is virtually enlarged image. This is final image. If this is object, this is a final image, that is A dash B dash, B double dash A double dash. Okay, so for this object the virtually enlarged image is obtained. Virtually enlarged image is obtained. So this is the final image distance, and this is least distance of distinction. Okay, So here we are going to find the magnifications. So the ordinary magnifications, the total magnification of this combination. Total magnification of this combination. Total magnification of this combination, that would be the product of the magnification of objective lens and the eye lens. So we have a two lens system, no? So for a two lens system, the total magnification of the combination is the product of the magnification of objective lens and the eye lens, magnification of the eye lens. Okay. So first we are going to find the objective of this magnification of objective lens. So magnification of objective lens, it is the ratio between height of image to height of an object. So this case, objective lens. So magnification of objective lenses, this is beta, then this also is beta. Okay. So magnification of objective lenses, ratio between height of image to height of an object. For this lens alone, for this lens, forget this lens. So first the eye lens, objective lens, this is the object, this is the image, and this is height of an object, and this is height of an image. Okay. So these ratios are equal, then automatically, which is equal? This is parallel to this, no? So L by F naught, because both also opposite angles, it is a concurrent. So we can say that H dash by H, which is equal to L by F naught. L by F naught. This is one equation. Also, we can prove this from tan angle. That is, tan angle is equal to opposite by adjacent. So in a tan, what is the opposite? It is what is the tan? Yes, H dash by L. H dash by L is equal to what you will get? H by F naught. H dash by L is equal to, this both also equal, no? See, this is a tan value. So opposite by adjacent, H dash by L is equal to, in this, H by F naught. H by F naught, or this is the magnification of objective lens. Also, which is equal to, we can exchange this both. This and that we can exchange. H dash by H is equal to L by F naught. So this two also the magnification of objective lens. So we found the magnification of objective lens. Similarly, we are going to find the magnification of eye lens. So how we are going to find, because the final image is at the normal near point. Final image is at normal near point. That is virtually enlarged image. Okay. So already we know the magnification of eye lens, that is equal to 1 plus, from this 1 plus d by Fe. But for angular magnification ME is equal to, it is only d by Fe. So it makes an angle, no, beta. So angular magnification of this eye lens, we found it. This is equation number 2. So this is 2 and this is 3. Substitute 2 and 3 in 1. What will you get? Substituting 2 and 3 in 1, the total magnification of this combination is MO into ME. That is magnification of objective lens and magnification of eye lens. So substituting the value, it is L by F naught into D by Fe. So this is the total magnification of a compound microscope. Okay. So finally we found the total magnification of the compound microscope. So in these cases we should choose the two different lenses. The objective lens should be taken with a short focal length and the eye lens should be taken larger focal length. And we know the least distance of distinction, that is 25 centimeters. Okay. So if the data are given, automatically we can find the magnification. Shall we solve the problem? We will solve a simple problem related to this. And I told already L. What is a L? It is a tube length. So L is the tube length between principal focus of objective lens to principal focus of eye lens. Okay. So this tube length is 20 centimeter. If tube length is 20 centimeter, okay, and first lens, objective lens focal length is 1 centimeter and eye lens focal length is 2 centimeter. Find the magnification. We can find easily. That is magnification, total magnification of this combination is equal to L by F naught into D by F E, no? So substitute the value. Tube length is given, that is 20 centimeter divided by focal length of objective lens is 1 centimeter into least distance of distinction is LDDV, that is 25 centimeter divided by focal length of eye lens, it is 2 centimeter. So centimeter cancel. This 2 and this 20, it is 10. So 10 into 25, which is equal to 250. Therefore, magnification of this case, it is 250. So 250 times that magnifies the object. So this is how we'll solve the numericals. Okay. I hope you are very clear. So this formula gives a total magnification of a compound lens, compound microscope. In the compound microscope, L is the tube length and FO is the focal length of objective lens, FE is the focal length of eye lens, D is the least distance of distinction. And objective focal length should be less than the eyepiece focal length. So we have a two different lens, but the combinations of total magnification would be greater. So one must want the larger magnification. He cannot use a simple microscope. He can use only the compound microscope with the tube lens, of some known value. Then the magnification would be higher. Okay, and it has some limitations. So what are the limitations it has? Some advantages or some limitations. The first limitations, to get the good quality, and visibility of image, the object should be illuminated. What is called illuminated? We'll do in the lab. So we'll keep a concave mirror at the bottom. The concave mirror faces the external light. Then it converges and passes through the slide. Then from the side, the objective lens and eye lens, it will be visualized clearly. Without light, we cannot get the clear image. So to get the good quality and the visibility of image, the object must be illuminated by a suitable converging mirror. Then the second one, in modern microscopes, multi-component lens system is used. In modern microscope, multi-component lens systems are used. For what? Why the multi-component lens system is used means to minimize the optical aberrations. Aberration means mistakes. Used to minimize or to reduce optical aberrations. That is called defects. Okay, these are the limitations. There are two limitations in the compound microscope. To get the clear image and for a good visible image, the object must be illuminated by suitable concave mirror. And in a modern microscopes, a multi-component lens systems are used. Why we are using a multi-component lens system? Because more the lens you use, more the optical aberration is minimized. Okay, then we'll get more clear image. So in the coming class, we are going to study about the telescopes and its types.